Okay, welcome everyone to my continuation of representation theory. Today's topic is maybe one of the most important notions in modular representation theory due to Brouwer and Nesbitt. So the defect or the defect group, we will see actually what it means. And this is really this idea that I was trying to sell in the blog video. If you haven't seen the blog video, it doesn't really matter. Well, actually it does, but we'll come back to it later. And it's this idea that you want to measure how far something is away from being semi-simple, and we already have the block decomposition. And I mentioned that kind of more complicated the blocks are, the further it is away from being semi-simple, and the measurement for complexity here is to call it the defect or the defect group. So let's have a look what it actually is. And I kind of the definitions are a bit tricky, so I kind of want to have an analogy in mind. And the analogy I have in mind is that there's a defect, which is a little bit like a Betty number of a manifold. And there's a homology, there is the defect group, which is more like the homology of a block, of a manifold. And kind of there's a really precise relationship to go from one to the other, basically by taking graded dimensions. But one of them is richer, but also homology is a bit tricky to define, why the Betty number is kind of okay to define. And the same kind of happens for the defect and the defect group. So the defect group is kind of a numerical invariant you throw at your block. And the defect is a numerical invariant, and the defect group is a group invariant that you throw at your block. And kind of decategorifying, if you want, the defect group gives you the defect in the very same way as taking the dimension right here from the Klein bottle, which has homology written down here. And if you take the dimension in an appropriate sense, this is of dimension 1, so you write a 1. This is of dimension 1, so you write a 1 as well. It's just shifted here in degree, so the t only keeps track of degree here. And this one is of dimension 0, so you don't get anything. Same here, 1, 1, you get the same answer. So in this case, the circle actually is different from the Klein bottle, obviously, of course. And homology can distinguish them, but the Betty numbers, the Poincaré polynomial that I call P here, which is really just Betty numbers, but you keep track of gradings. The Poincaré polynomial can't. And it's kind of very similar in the story of defect and defect group. On the other hand, the polynomial or the Betty numbers are just much easier, and the homology is a bit, it falls a little bit out of the blue. And kind of the same will happen here for defect and defect group. Right? So that's my analogy. Some numerical measurement of complexity and some more sophisticated measurement of complexity comparable to Betty numbers and homology for manifolds, just in the setup of blocks. Remember that we had this block decomposition, and what you do now is the following. Again, everything is super easy to compute via Magma, which is linked in the description, and you can just run it yourself online. Whatever. So I list here, I hope this example is by now familiar enough, the character table of S3, either over the complex numbers or the Brouwer characters over F2. We're just crossing out the corresponding little bit weird looking conjugacy clause in characteristic 2. And I list the blocks, and this was what we got last time as the blocks. So the first two, which are equal as Brouwer characters, they are nicely arranged in blocks, and the third one is the second is which its own block, and the defect is 1, 0. So this is of defect 1 and this is of defect 0. And the defect is defined as follows. It's basically the biggest prime power that divides you over the block, if you want. And the formal definition works as follows. So you can decompose your group, well, the order of your group, into p to some power, and everything that's not divisible by p. We have this A, and the defect is just the biggest number. The smallest number. It's kind of everything is reversed. It's a small, in order to have complexity going upwards, you kind of need to reverse everything. Anyway, it's the smallest number such that P to this power divides the Brouwer character for all simples at 1, which is just the dimension of those. So it's the definition of a defect is basically the biggest power of P. Well, the defect is this negative nonsense. Let's ignore that. The biggest power of P that divides the dimension of the simples in the block. Yeah. So in particular, well, it turns out that this is a really good measurement. So the defect is 0. A bit confusing. I say it again because the defect counts backwards. 2 is the biggest power well, because 6, of course, 2 times 3. So 2 is the biggest power we would expect to divide our modules. So the defect is minimal because the biggest power works. So defect measures this difference between the biggest power and what actually is. And for the other one, well, the dimensions are 1. So the defect is 1 because the power is 0. So it should be p to the 1 minus 1 in order to make it work. So the only confusing part, I'm always confused, is that the defect counts backwards from the biggest power that should divide your dimensions to what actually divides your dimensions. And that kind of measures the complexity in the setup. It's kind of a cool idea in some sense. Okay, the definition of a defect group is a bit opaque. Let me just say, so in the end, the only thing you need to know is that there's a group that you can associate to every block, and Magma can compute this group for you. I'm going to show you some code in a second. But basically, it works as follows. You have the block decomposition, and one point of the construction, so that's just copied from last time, and one point of the construction were the idempotents corresponding to the blocks. And the defect group is kind of the biggest group, the biggest maximal group, maximal in the sense that the block idempotent is detected by D, the defect group. In the following way, well, it's just what it looks like. This is just the formula. Kind of you can ignore it. The point is you can express your idempotent as a linear combination of group elements by definition of the group ring, basically. And you can restrict to certain subsets determined by a subgroup. And if this expression is not 0, I say that the idempotent is detected by the subgroup. So you might, like you have an idempotent, and there might be some coefficient showing up, but they might not exist in your subgroup. So in this case, the expression would be 0. Or they might exist, in which case the expression is not 0. If it's not 0, it's detected. And the block is kind of the biggest one that still detects your idempotent corresponding to the block. The biggest subgroup that still detects your idempotent. So it basically is the biggest subgroup where the expression of your idempotent that picks out the block is still valid. That's the definition of the defect group. And it's an invariant of the block in the following sense. And it really is this analogy of homology and or the characteristic or Poincare polynomial. So defect groups exist in their unique approximation, which is not obvious at all. I'll give you some examples in a second. And they have always order p to the d, where d is the defect. So in this sense, right, going from homology, you take the dimension and you go to the Poincare polynomial. And from the defect group, you take the size if you want, just the power of p that appears, and you get the defect, right? But for example, you can't distinguish those two groups because they're both of order p squared. So they both have defect 2, but well, they could be different defect groups. So it's really a finite structure. It's very same story as for homology. And that's why people, because it's unique up to conjugation, people call it the defect group. Also, well, formally speaking, a defect group would be more correct, but it's a unique up to conjugation anyway. So let me go through some examples, and then, well, there's some Magma code that you can run that computes defect groups. So I've done it here, again, for the symmetric group, in this case, characteristic 2. Anyway, so the defect group, defect 0, and then the defect group needs to be a group of order p to the 0, so of order 1. I don't know many groups of order 1, so it's always, a defect group is always trivial, and this is kind of the case of semi-simple, so everything should be easy, and yep, the easiest group I can imagine is a trivial group, so it works pretty well. So defect 1 means my group needs to be of order p to the 1, so it's prime order, and there are not many groups of prime order, there's exactly one. And yeah, so the defect group is always Z mod P in this case, which is still a reasonably easy group, right? So it's not very far away from semi-simple. For defect 2, kind of the same reason, you have now P squared. So the only groups of order P squared are those two. So it's either of those. So that's the defect group. And from P cubed onwards, it gets way more complicated. And the distinction is not as easy anymore as saying, okay, it's either, it's not necessarily, for example, it's not necessarily a billion or something. So defect groups basically can get arbitrarily complicated. But this is just a small list of examples. So d equals 0, trivial, d equals 1, a little bit more complicated, d equals 2, a little bit more complicated, and so on. It really measures the complexity of your block, and therefore the complexity of how far the representation theory is from being semi-simple. And it's really, really the same in some sense, at least in this analogy. It's the same as for homology and topology and co. So if you want to classify zero-dimensional manifolds, you can do it. It's not so bad. The zero-dimensional manifolds or zero-dimensional topological spaces, actually, just to collectional points. Let's say dimension makes sense. Dimension 1 is already a bit nasty. So basically, one-dimensional topological spaces should be graphs. That's not so bad. But then you have some sometimes really ill-behaved examples here. What is called the Warsaw circle. A very complicated topological space, which is still one-dimensional in a certain sense. So dimension 1 is already really a nasty setup. And classifying topological spaces in higher dimensions, yeah, well, let's just say well. And it's very similar for blocks. So the blocks with trivial defect are always matrices and are just fully classified. So defect 0 or defect group trivial is easy. And the cyclic defect groups, that's defect 1, you can actually almost classify the blocks. So you basically write down a list of potential algebras that you see, and your algebra will be on that list, right? And the list is finite. It's just a bit hard to decide what algebras you see. And beyond that, I think not really much is known. It really, really is a similar picture. So there are many conjectures related to various types of defect groups abelian or whatever. But these are always very, very hard questions, and very, very similar as this analogy to topology. Anyway, by the way, I hope you like this analogy to topology, like the block and the defect group, and the defect is a little bit like homology and Betty numbers in a very similar way. So you can go from one to the other using a pretty trivial operation, but going back is certainly not in any way obvious. It, of course, doesn't work because you have many choices involved. Anyway, so I hope you enjoyed this analogy. I hope you liked the video, and I also hope to see you next time.